Hi, in this fourth lecture, we shall look at the mathematical notion of infinity. It is at once an application of the concepts we've been discussing in previous lectures, as well as laying the foundation for some of the next topics that will involve infinity in various ways. We begin by looking at what infinitely large sets are mathematically, and also why we as computer scientists care about them. First off, we need to realize that, as far as we know, everything in the universe is finite, and that most definitely includes our computers. No matter how much memory or hard disk space they have, no matter how big of a cloud they might be connected to, at the end of the day, they are and always will be finite machines, executing programs for a finite amount of time. So, if this is about mathematics for computing, it does seem fair to ask, why do we even care about infinity at all? As far as computer science as a field is concerned, there are typically two types of answers related to the use of the infinite as a model of two kinds of phenomena computer scientists frequently deal with. The first is as a way to approximate an awful lot. That is, quantities that are, of course, finite, but are so big that for most practical applications we don't expect to deal with their limits as part of normal operation, but rather in the form of an error or exception. The second is to model the absence of a known finite bound. In many cases, for example, when computers process data as it comes in, sensor data in an engine control unit, for example, or video streams during an online conference, there is no known maximal amount of data or a maximal amount of time the computer is processing it. The algorithm runs as long as the computer is on and data is coming in. In addition to mattering to computer science in various ways, infinity also matters to the structure of this course. For one thing, infinity is an integral part of the math toolbox this course is about. It's just one of its properties, and as professionals, it behooves us to know the tools we're using. Also, it is an application of the math concepts we've gotten to know so far, using a fairly simple notion of set, relation, and function. We can drill into the mathematical concept of the infinite and gain a few insights about it that are maybe not completely obvious from the start, perhaps even surprising. Some of those ideas might even rub against your intuition of how things are supposed to be, and if they do, you should know that you aren't alone in this. Even the people who discovered some of these ideas and were really the first humans to ever investigate mathematical infinity in a principled manner had a hard time believing what they found. When Cantor made such a discovery, he shared a sense of befuddlement with Dedekind with this quote, where he says, "I see it, but I don't believe it." If people like Cantor and Dedekind, both of whom we shall meet again soon, stumble over their mathematical intuitions, we shouldn't feel bad if that happens to us too. Learning something that seems counterintuitive often evokes a kind of impulsive rejection, a dismissal because of a lack of plausibility. In reality, this state of cognitive dissonance that one feels on such occasions is the best opportunity to learn a deep, new truth, assuming, of course, that the new thing is in fact true and that it is not counterintuitive because it is actually wrong. It is an opportunity to update an intuition that has been stretched and extrapolated beyond the domain it was working in. That's part of what this lecture is, an upgrade package for your intuition about how numbers work, for numbers describing infinite quantities. Let us start with a simple problem. You know, of course, the natural numbers. A Boolean function on the natural numbers is one that assigns every natural number a value from a set of two elements. Let's call them true and false. It could be 1 and 0 or any other two values. That does not matter to our discussion here. So a Boolean function on the natural numbers is a thing that takes a natural number in and produces true or false as output. Let us also imagine an infinite computer. Infinite memory, it's infinitely fast, no limitations on word size, etc., etc. In other words, we're not interested in the physical limitations of the computing machinery. Imagine a quantum computer, or a magic wand if you like. As long as it can be programmed in some programming language, let's say L, with programs being arbitrarily long but finite strings of some finite alphabet or set of characters. The question we're interested in is this. Is it possible to create a language L such that every Boolean function on the natural numbers can be expressed in it? It may be that such a language exists already, maybe Java is such a language, but we're not even concerned with that, and we also don't care about its features and capabilities. We simply ask whether it might be possible for such a language to exist. To put this into the lingo of sets and functions, if L is the set of all valid programs in our hypothetical language, and 2 to the n is the set of all functions from the natural numbers to a two-valued set, could there be a surjective function that maps the programs in L to the functions expressed by them? You might want to ponder this for a moment. At the end of this topic, we'll answer this question by comparing the cardinalities of the two sets, L and 2 to the n. Let's start now with how infinite sets are defined. There are a number of different definitions, but this one by Dedekind is one of the most elegant. It says that a set is infinite if and only if it is equinumerous to a proper subset of itself. This might at first sound slightly paradoxical. After all, you get a proper subset of some set A by taking elements away from A. So how could the resulting set contain the same number of elements as A? If that's how you feel, forget about that intuition for a moment and see if you can apply the idea in spite of it. Start with the natural numbers. We know them to be infinite, so they should meet that definition. Start by defining a proper subset of n. Obviously, any set of natural numbers other than n itself would work, but keep in mind that the set must be equinumerous to n itself, so a finite subset will not do. Define an infinite subset of n, and then show that it is equinumerous to all of n by constructing a bijection between it and the natural numbers. Here are some possible answers using the positive natural numbers and the even numbers as proper subsets. Okay, so the natural numbers meet the definition of an infinite set, as we would expect. In fact, the natural numbers and anything that is equinumerous to them are called countable or denumerable. Countable sets are very important to computer science because our current computing machines are computing by making sequences of discrete steps, one after the other, which is nicely modeled by enumeration of a set through a bijection with the natural numbers. Countable sets are also the smallest infinite sets, which is not something we're going to prove in this lecture. The cardinality of the natural numbers and all countable sets cannot, of course, be a natural number itself, since each of those denotes a finite quantity. Instead of a string of digits, therefore, it needs a different name, which is, in this case, the Hebrew letter Aleph with the index 0, pronounced Aleph 0 or Aleph naught. Cardinal numbers representing the size of infinite sets are called transfinite cardinal numbers, and Aleph 0 is the smallest of them.